First of all, let's look at this question and let's look at the equations that we're going to use. Well, we've got a balanced equation. We know that 1 mole of the alcohol reacts with 1 mole of the carboxylic acid. So there they are, reacting on a 1-to-1 ratio. We also can work out the MR of each of those molecules. So the MR of the alcohol, if we add everything together, is 118. And the MR of the carboxylic acid comes out to be 146. What we also know is that percentage yield is equal to the actual amount you obtain divided by the calculated or theoretical. So get everything down that you know times by 100. So let's now calculate the. So you may wonder here why I've times by 10 to the minus by 10 to the 3. Well, that is because the density is in grams per centimetres cubed and the volume was in decimeters cubed. You must convert to the same units, so I've times by 1,000 to get the volume into centimetres cubed. So that answer there comes out to be 1154 grams of alcohol. So we've now got our mass of alcohol. We have the mass of the carboxylic acid. It tells us there it's 0.930. I'm going to convert that to grams because that's in grams. So times that by 1,000, that's 930 grams of compound F. So that's F, and there's the alcohol. So what I'm going to do next is to do the ratio of the alcohol versus the acid in order to calculate the moles of acid that I should be getting. Mass in grams, MR, grams per mole, and amount in moles. So what do we have here? We have the mass of the alcohol is 1154 grams. The mass of the acid is 930 grams. The MR of the alcohol is 118.0. The MR of the acid is 146.0. And therefore, the number of moles of alcohol that we obtained is mass. Don't forget to tell the examiner you've done mass over MR. It's 1154 over 118. And the moles of the alcohol of the carboxylic acid, mass over MR, is 930 over 146.0. So the number of moles of the acid is 6.37, and the number of moles of the alcohol comes out to 9.78. Theoretically, we should be getting exactly the same moles of acid as alcohol because they react in a 1-to-1 ratio, but we haven't. We've only got that many moles, so that is the actual moles, and this is the calculated. So now we can whiz on to calculating our percentage yield, which equals the actual over the calculated, which is 6.37 all over 9.78, times that by 100%. So the percentage yield should come out to 65.1%, 3 significant figures. So in this question it tells you that the reason why you never get 100% yield is that you get side reactions where you're getting other compounds produced. If you remember back to the alkanes, you know that in order to separate liquids that mix, the only way you can separate them is by a process called fractional, not just distillation, fractional distillation. If there's more than 2 liquids, you can't just do it by ordinary simple distillation because there's quite a few other liquids. So when you come to explain the apparatus, what you must do is have with you a sharp pencil and hopefully a ruler. So if we put our ruler onto here, we now need to draw the condenser, and the condenser is a thin tube, and that tube is surrounded by a jacket where the water flows in a separate contained unit. So that jacket, let's come round here, that joins onto there. So in this case you've got water going in at the bottom and water leaving out at the top. So this thing here is your condenser, so label it. The distillate, that's the liquid that's leaving, therefore goes through the middle tube. What you then have is you need to have a fractionating column. So the fractionating column, remember, has got a temperature gradient. So you need to draw a long tube. And at the bottom of the long tube is the vessel that contains your mixture of liquids of different boiling points. So that's called your fractionating column. And usually it's got little bumps on it to increase the surface area. Now, in order to identify the fractions, you need to measure their boiling points. At the top, you need a thermometer. And you need some anti-bumping granules in there to stop big bubbles forming. Now when you're going to heat this apparatus, it needs to be secured. So that can sit on a gauze on top of a tripod. Do not draw a Bunsen burner. That's going to be heated from below. The vapours will then rise. Let's have some nice vapours here. The vapours will rise up the column, and the temperature gradient, so as you're going to the top, it's hotter at the bottom and it's cooler at the top. And therefore you're going to get more volatile liquids rising, and as they reach the top and start to pass down the condenser, they start to cool and condense from a vapour back to liquid, where they come off as the distillate. So make sure that your thermometer bulb is right over where the vapours are about to condense. Now check your apparatus for leaks, that everything is sealed and that the vapour can actually pass through, that the jacket is sealed and that the water can get in at the bottom and out at the top. So the molecular formula of H is, there's carbon 1 there, and remember the benzene ring contains 6 carbons. There's another one there and another one there, so that's C9. We had all the hydrogens up, there's 3 here and 1 each on the benzene ring, don't forget those little guys. So that's 3, 4, 5, 6, 7, 8, 9, 10. And 1 oxygen. Let's number the positions on our benzene ring. 1, 2, 3, 4. So you can see here the acyl group is bound to carbon 4, but there's nothing stopping it on going on position 3 or position 2. There's also position 2 there and 3 because they're identical. So you could have either put the acyl group on position 2 or position 3 to get what's called a position isomer. So let's have it going on position 3. Examiners tend to be very lazy, and this question has come up for the last 10-20 years. So question wants you to outline, name and outline, so I'm going to highlight that so I don't forget. Name, outline the mechanism for the reaction of ethanol chloride with methylbenzene to produce molecule H. Seem to have forgotten what molecule H is. I'm just going to skip backward. Now I remember what H is, so I'm going to draw H again. So H just happens to be a methyl group on position 1 of the benzene ring, and there was an acyl group on position 4. So I've reminded myself, so that's CH3, what molecule H was. So include an equation for the formation of the reactive intermediate that is involved in the reaction. So reactive intermediate, well, benzene, because it's got that ring there, is attacked by electrophiles. So we need to show the formation of the electrophile, and the electrophile must have a positive charge. So that is when ethanoyl chloride reacts. So to get the intermediate, we've got ethanoyl chloride, which is CH3COCl. Remember that reacts with the halogen carrier AlCl3, which removes the halogen from it. The reactive intermediate, remember, is your acylium ion, and aluminium chloride AlCl3 becomes AlCl4. Don't forget it's negative charge. So the reactive intermediate is your acylium ion. The name of the mechanism, well, benzene is attacked by electrophiles, so it must be electrophilic. The benzene ring is reinstated. All that happens is these little hydrogens here get substituted, so it's electrophilic substitution. So let's now look at the mechanism. So we want ethanol chloride and methyl benzene to produce H. So remember, it's methyl benzene and not benzene. Don't forget your methyl group sitting on top. This is the electrophile, the acylium ion. So I'm just going to draw it out. So I make sure that the right atoms attack. So there's my positive charge on the acylium ion. So in this case, not to forget that pair of electrons is dragged out of the benzene ring by the electrophile. So a bond is now being formed with one of the positions on the benzene ring to here. Now ultimately we want our acyl group to end up on position 4, so don't plop it anywhere else. And don't forget that the benzene ring donates a pair of electrons, so for one point in time the ring is broken. Now, because it's going on to position 4 here, the broken ring must not extend beyond positions 3. There's your positive charge you localise around the ring. Don't forget there's still a little hydrogen hanging on that's going to get substituted. And here is the C double bond O, CH3. So to finish off your mechanism, that hydrogen restores the 6 electrons into the benzene ring. And there's your product, and don't forget that little H plus ion is thrown out. In this question here, it was just a process of deduction. You were told that you had 2 amino acids, so you had a tripeptide. So you had a dipeptide, so you've got cysteine, aspartic acid, and remember if you've got 2 amino acids, they could be arranged in 2 possible ways. So here is the peptide link, and the only difference is this is the cysteine amino acid and that's the aspartic acid. So if we look for the centre of the amino acid, there's the centre of the amino acid, the chiral centre. You can see here, there's your hydrogen, and therefore this here must be the side chain. So there's the side chain of the cysteine, and there's the side chain of the aspartic acid. So there's your asp. So if you hydrolyse those dipeptides, you'll end up with aspartame and cysteine, aspartic acid and cysteine. So the next question says, a mixture of the 2 dipeptides, J and K, is analysed by gas chromatography, shown in the last slide, and then followed by mass spectrometry. So it's called gas chromatography, mass spectrometry. So Y, J and K can be separated by gas chromatography, and why is mass spectrometry using electrospray ionisation? Why can't we identify them? So gas chromatography explanation, as mentioned in the last slide, is the dipeptides would have different affinities for the mobile phase, or you could have said the stationary phase, and therefore can be separated. However, you must notice its 4 marks. So notice that we've probably got 1 mark there. So therefore you need to mention that one of the dipeptides would have a shorter retention time on the column. So I'll use other mark. Mass spectrometry explanation is even easier. If you work it out, remember mass spectrometry measures mass to charge ratio. And if you're ionising them using electrospray ionisation, so remember there's your molecule. In electrospray you're adding protons to get the charged particles. So there's your dipeptide that's protonated. Both of them have got exactly the same identical MR, and therefore their peaks would be identical. This question showed the importance of taking a ruler with millimetres into the exam, because you had to measure the ratio of the distance moved by the solute and the distance travelled by the solvent, because we know that the RF value here is equal to the distance travelled by your solute from where it starts from to where it goes to, divided by the distance travelled by the solvent front. That gives you your relative front value. So the first spot corresponded to the dipeptide Sir Allah. It had an RF value of approximately 0.15, and therefore your dipeptide was Sir Allah. Spot N had an RS value equal to that of the alanine lysine dipeptide of 0.5, so it was the alanine lysine dipeptide. Using a process of deduction, therefore, alanine is common to both of them, and that must have been the central amino acid, so therefore the sequence must have been serine, alanine and lysine. Those of you who do biology know that if you look at base pairing in DNA, you know that the backbone is sugar, phosphate, and sticking off the sugars are bases, which are adenine, guanine, cytosine and thymine. And you also know from biology that there are 3 hydrogen bonds, potentially 3 hydrogen bonds on a guanine base, and the corresponding base, cytosine, can form 3 hydrogen bonds at beautifully equidistant from the guanine, and therefore that's why the two always pair together. Adenosine and thymine can only form 2 hydrogen bonds per molecule, and that's why they always base pair together. So as it's once been said, 2 for T, T for 2. So thymine always forms 2 bonds, whereas G and C form 3 hydrogen bonds. The next question asks why urea was effective at separating the complementary strands in DNA. Well, if we look at the base structure of guanine, you can see that guanine has the potential to form 3 hydrogen bonds. Let's show the dipoles on there. So you've got a lone pair on the oxygen, you've got an extremely electron deficient hydrogen here, and extremely electron deficient hydrogen here. If we now look at the urea molecule, you can see it possesses 2 lone pairs. So let's now position the urea molecule opposite the guanine molecule. And you can now see why it would disrupt the hydrogen bonding and bind using hydrogen bonds to a base. So it would stop the DNA rezipping. How would you answer that? You could say that the amino groups donate lone pairs to electron deficient hydrogens on the base. Picture paints 1,000 words. I prefer this explanation. So in this question, you should have just got your calculator, and you should have been able to get your calculator and take the natural log of the rate constant. And you'd notice that as the rate constant increases, the natural log of the rate constant also gets less negative. So you then had to plot a graph of the natural log of the rate constant versus 1 over the temperature. And that's on the next page. If you've got a graph that does this, you know you've done something seriously wrong, and that's probably because you've got your scale upside down, and it's probably going from -10 down to -1, which is completely wrong. So you know when you've plotted your graph of the rate constant versus 1 over temperature, that it's actually got a negative gradient. Now we also know that the gradient is equal to minus EA over R. How do we know that? Because if we look at a straight line graph and we look at a straight line, the general equation for a straight line graph, y equals mx plus c. C is the intercept here. M is the gradient, and x is the axis, which is 1 over t, and y is the natural log of k. So, if we now look at what we need to do with our graph, we need to use this data, plot the graph onto the point, and then we need to apply it to the equation. So if we now move on to the next slide. Make sure when you plot your graph, you've got the equation underneath it and the correct units. In this case, I think the units were already given to you. Now to calculate the gradient, that was quite simple because it's a straight line graph. Go on to the next slide. So to get the gradient, first of all, we'll look at the change in y. So it's quite simple if we take the two furthest points from each other, which was minus 4.8 minus a minus 10. That gives us minus 6.9. To get delta x, take the two furthest points here, and that is 0.24. Don't forget that is times 10 to the 3. So therefore the gradient delta y over delta x equals 6.9 over 0.24 times 10 to the 3. So the gradient is equal to minus 2.88 times 10 to the power 4. Since the gradient is equal to EA over R, which equals minus 2.88 times 10 to the 4, where R is the gas constant, and the gas constant is 8.314, EA equals minus 2.88 times 10 to the 4 times the gas constant 8.31, and that comes out to, well, that was minus E8, so minus E8 equals, so therefore the activation enthalpy is equal to 239 times 10 to the 3 joules, which equals plus 239 kilojoules per mole. Notice if you don't get a positive value for your activation enthalpy, you know you've gone wrong somewhere, because activation enthalpies are always endothermic. Now also the answer should be to 3 significant figures.